All right, with that, we are ready for our next talk. And for that, I'd like to invite our next speaker, Haichen. Haichen is going to be talking about how zkRollups and zkEVMs work, especially from the context of how Scroll is designing it. And you can already saw him talk about all the prizes they're giving. We already saw a lot of talks around how to think about these technologies as rollups become more and more common. And we're going to go into a lot more depth here now. So without further ado, I'd like to welcome him on stage and get started. So welcome, Haichen. It's great to have you here again.
Yeah, thank you, Kartik, for the introduction. And thank you for having me here to present to all of the people in the scope and then scaling Ethereum event.
We're excited. So I'll let you take it from here and all the best.
Okay, cool. Hello, everyone. I'm Haichen from Scroll. So today I'm going to give a introduction to the zkRollup and then the zkEVM. And I'm going to we just introduce like how the zkEVM is built, and then what is zkEVM is going to prove. So give like a little bit more insights of like how we are building the zkEVM from the Scroll. Okay, so first of all, like we all know Ethereum is great because it's decentralized and secure, and it has a humongous of community and developers are building on top of that. But Ethereum also has its own problem that it's not built to be scalable. So to handle like thousands of transactions per second. So this is because of the blockchain trilemma, that one blockchain cannot achieve scalability, decentralization, and security at the same time. And we all know so decentralization means that the chain can run without any trust dependencies on a small group of centralized actors. And this is typically interpreted as to be like not trusted by any set of nodes. And security means like you can sustain the attack from a large proportion of the nodes running the inside the networks. And the scalability just means that the blockchain can process more transactions than a single node. And we know that the Ethereum and other like the traditional blockchain, for example, Bitcoin, they all prioritize the decentralization and security, and such that it both suffer from the scalability issues. So to take a deep, closer look at why Ethereum or like other blockchains is not scalable, it's because like we can show like this, like a diagram of this how Ethereum works. So users send transactions to an Ethereum node, and then the transaction will then be broadcasted to a P2P networks. The proposers then will submit a block, then everyone in the network will download this block and re-execute all of transactions inside this block to reach consensus. So that means like all of the full nodes need to do the same thing, like same computation for every blocks. And because the Ethereum is widely decentralized, so hundreds of thousands of nodes will repeatedly doing the same computation for every block. And that's why the Ethereum is not like built for scalable, because it sacrificed some like it has a lot of redundancies in computation just for being resistant and being censorship resistant, and then also being decentralized. So how does the Ethereum community plan to solve the scalability problems? So about 2.5 years ago, Vitalik posted this blog post on the forum about this Rollup-centric roadmap. So the plan is to scale the Ethereum through the Rollup chains that can process more transactions on the layer 2, but having the efficient settlement and finalization on the layer 1 to achieve the scalability and without sacrificing lots of the securities for that. So now let's take a look at how the Rollup works in general. So here now you have two chains. The first, the layer 1 being the Ethereum, it serves as the settlement layers for any transaction happen on the layer 2s. And then the layer 2 becomes a less decentralized blockchain, so that it can process more transactions and blocks at a faster pace. And periodically, the layer 2 will batch all of transactions and send sufficient data to the layer 1 with some sort of the proof to finalize all of the transactions that in this batch happen on layer 2s. So the requirement for a rollup to be a rollup is that the users can recover the latest state root on the layer 2, purely relying on the data stored in the layer 1s. And then there are two types of the rollups right now. So one is the optimistic Rollup and the other is the zkRollup. So I'll give like first some of the intro like about what is the optimistic Rollup. So the optimistic Rollup is that it will just submit the transaction data to the layer 1, waiting for a period of time for the challenges. So if no one challenged like there is any invalid transaction within that batch for a certain period of time, then that batch of transaction will be considered finalized on the layer 1 and it cannot be reverted anymore. However, the drawback of this optimistic Rollup approach is that the waiting period time is quite long. So that people need to wait for 7 days until that transaction can be considered as finalized on the layer 1. So that's why like the people will like tend to work on another type of Rollup. It's called a zkRollup. And in the zkRollup, every time like you will not only submit the data to the layer 1, but it will also accompany with a zk proof that can be easily and cheaply verified on the layer 1. And once this proof is verified by a smart contract on the Ethereum, and then that batch of transactions can be then finalized. That's how like you achieve fast finality for the zkRollup with the zkRollup. So, but like let's simplify the diagram a little bit. So for the zkRollups, so basically you need to, on the layer 2, you need to build a prover that's going to generate a zk proof and then accompany with some data, and then both were submitted to the layer 1 for settlement and finalizations. But the problem with the zkRollup is that it is non-trivial to build a zkRollup system for many reasons. So first is that to generate a proof for some computations, you need to write down your program logic in the form of arithmetic circuit. And it's quite complicated and hard to being like using only the additions, multiplications, and some of the math assertions in the circuit to express your computation, your program logics. And also it requires certain overhead to handle like to generate this zk proof for the zkRollups. And also like even worse that different programs and different applications may have a different circuit, such that like you need to encode every application you need to write a new circuit to be able to using the zkRollups. And even worse that there will be no composability between the different application-specific zkRollups. How to solve this problem of this no composability with different application-specific zkRollup is that we need to build a general-purpose zkRollup that can run any type of applications. And then one of the type is like you can where we are building is called zkEVM. What we do is trying to put the Ethereum virtual machines into a zk circuit, so that any application, any dApps that are written using the Solidity like built on top of the Ethereum can be run directly on the layer 2s, and then using the zkEVM to generate the zk proof for that any applications that deploy on the layer 2s. So that's the benefit of having the zkEVM in the layer 2 in the zkRollup, is that you can achieve the composability and it being also very developer friendly, because all the developer need to know is still the Solidity and using the same tool chains, Foundry, Hard Hat, anything like you're using on the layer 1s, you can also using on the layer 2s. But there are also some drawbacks for building the zkEVM. So one reason is it's very hard to build. So the Ethereum virtual machines is not built for the zk, so it's not very zk friendly. So you need to be very careful, and a lot of like and it's very hard to build like putting the entire Ethereum virtual machines into the zk proof. And then due to like this incompatibility of the basic field with the finite field you're using in the zero knowledge proof, and also there's a lot of special opcodes like cat track, some bitwise operations, and also the signature verifications, the ECDSA signature verification. They are all quite special functions, like, and they need to spend a lot of effort to building the zk circuit. And also to generate the proof for the zkEVM, there's quite large proving overhead for that. So that's why like initially people are more tends to building the application specific zkRollup instead of building the zkEVM. So why is the zkEVM possible now? So there are mainly three reasons. First, we are not having better zero knowledge proof systems. We have like a lot of new primitives such as the polynomial commitments, the custom gates, lookup arguments, and the recursive proofs. All those like recent advancements in the zero-knowledge proof protocols that makes the building the zkEVM more practically available, like viable. And the second, we have more hardware acceleration available. We have right now like the more and more like the state-of-art GPU proof algorithms, and then we also we're expecting the FPGA or ASIC, some accelerator, zk accelerator solutions in the future that can further bring down the cost of generating a zk proof. And the third is that we have a lot of new open source toolings and frameworks available. And also, like not to mention, like the Scroll is building the zkEVM in the open source communities with the Ethereum Foundation, like the PSC team from the Ethereum Foundation and other open source communities. So there's lots of tools and resources available in the open source. So that's making the zkEVM building like the viable and practical. So now let's dive in deep into a little bit like about zkEVM. So there's like a few different zkEVM flavors, which they all call the zkEVM. So first is language level compatibility with the Ethereums. So that means like you can compile some EVM friendly language like Solidity or Euro into a snark friendly VM, which differs from the EVMs. And the second is bytecode level, which you directly interpret the EVM bytecode directly inside your zk circuit, so that you don't need to use a different compilers. You can reuse all the same tool chains to directly use that, and then you can run on the zkEVM. And then the last one would be the consensus level, which is target for the full equivalence as the with the EVM using on the layer ones. That means that this level zkEVM can directly prove any layer one blocks. And here, like what we are building in the Scroll is that we're trying to target for a bytecode level compatible or equivalent zkEVM, such that like the developers can using all of the existing tools to building on top of the Scroll. Okay, now next we're going to talk more about the zkEVM. And first, let's focus on what the zkEVM trying to prove. So let's simplify the Ethereum like or the EVM how it works. So first of all, at one time step like T, you have like a state root trees that including all of the state account informations and also the any storage trees stored in the smart contracts. And at that time, you'll receive a new transactions and trying to do any like the transfers or executing some smart contracts. So you'll input these two as the input to the Ethereum virtual machines that are going to execute, and the output, the result will be a new world state with a different root after you apply the transactions. And then looking inside what happens inside the Ethereum virtual machine, you'll basically get like a few different modules. First, you have a state machine that's going to interpret all of the bytecodes inside your inside any smart contracts. And you have stack and a memory for any transient data keeping the memory. And also you will access to two databases. One is the bytecode database. Are going to load the smart contract from that and execute them. And the second, you have a storage database that going to keep any state account informations as well as like any storage like the stored in the smart contract. So let's like take one further step into looking at what happens like when you're executing the smart contract. So after you give like these two inputs, the world state and then the transaction to the Ethereum virtual machines, and then what it happens that you are going to execute opcode by opcode written inside the smart contract, and it will end up with a execution trace with different steps. For example, like it will do the push and then some push and then some mstore, mload, and then you do like the load some call data on the transactions and then execute like any specific logic from the smart contract. That will be finally ends up like modifying some data in the storage and in the state account tree. That will be generate a new state, world state. So now what zkEVM trying to do, like to add like the additional steps inside this, like the whole pipeline of the executions, is that the zkEVM is taking the specification of the Ethereum virtual machines, and then it will take also the same input data from the how the Ethereum virtual machine does is take a world state snapshot and then taking any new transactions as the input data. And what it's going to prove is that it's going to prove this execution trace generated from the Ethereum virtual machines is correct, and it will also prove that the state root will transit from the old state root to the new state root. So to summarize a little bit, like what does Ethereum is trying to prove is like you first need to prove the execution trace generated by running the Ethereum virtual machine is correct and unique. And the second, that you need to prove the global state root transit from the old root to the new root. Okay, so this is like some high level, like the things about what zkEVM is going to prove. And then let's dive a little deep into how we build the zkEVM in the circuit. So remind that I just explained that the zkEVM is trying to prove that the execution trace is correct with like after applying certain transactions and then executing some smart contract. So that would be, the logic is quite similar to what happens inside the circuit, where the core circuit in the zkEVM that we're building is called EVM circuit. The EVM circuit is basically a state machines mimic the state machine inside the Ethereum virtual machines. So you are also mapping all of the steps inside your execution trace into your circuit, which looks like just in this like the blue table, it'll be just looking like a two-dimensional matrix, and then each step will map to a slot inside the circuit as well. So like one-to-one mappings to the steps, and then one step will be corresponding to any opcodes you are executing inside the execution trace. So each step inside the circuit will having slightly different height due to the complexity of different opcodes. For example, the multiply opcode from the EVM maybe like it's more complicated than an add opcode. So it may be taking more rows and more resources in the circuit to prove the correctness of that opcode. And then if you take a closer look at each step slot inside the circuit, you will be separated into different sections or So you'll be having the step contact, keeping some context of like the stack pointers, the program counters, so the informations. And the second will be a case switch. I'm going to switch on different opcode specific constraints. For example, there will be like the one case for each opcode corresponding to like the two opcodes you have inside the Ethereum virtual machines. But this is basically a switch statement like you written inside any languages. And then the third section will be any opcode specific witness that are going to help you to prove the correctness of any opcode. Yeah, it's like I just explained, like for the step context, you're keeping certain information that for this current step is. For example, which code hash are you executing? Like it decides like which contract you are executing, and then some guess like you left it in the transactions, the program counter, stack pointer, and the current state root, etc. Like there will be more information. And then for the case switch, it will be basically a bunch of selectors corresponding to each opcode in the Ethereum virtual machines, and also different error cases. That's also important that you need to handle. You need to prove and handle all possible errors that will happen when executing the transactions. And also, we need to make sure that exactly only one case is switched on under each step. And the last one will be some opcode specific witnesses. Will be like some of the input data, for example, like the word like you're going to add together, and then the results you can go and do. And then there will be also some additional witness that are going to help you to prove the correctness of each opcode. So let's take an add opcode as an example to see what happens inside the in the zkEVM constraints. So first of all, you need to constrain the step context is transit correctly from the previous steps. So for example, in the current step, if I'm executing an add opcode, so the program counter, the next step program counter will be increased by 1 from the current step. And then the step pointer will shrink by 1 because the add opcode pops two words from the stack and then push 1 back to the stack. And then the gas left will be like reduced by 3 because the add opcode will consume 3 gas in the EVM. And second, it will be a case switch. That means like only one of the case, like one of the case will be selected. We just add here. So that means like so first you need to prove each opcode will be the selector will be 0 or 1, and then finally you need constraint like all of them sum equal to 1. And then last will be some opcode specific witness here. Is that, for example, because of this field incompatibility between the circuit and then the EVM. So the EVM word has 256 bits, but inside the circuit you can represent a value up to 253 bits. So that's why you need to break down the those words into two parts, like with the high 128 8-bit and then low 128 8-bit values. And then so you need to do like additions. For example, you need to say like for the low 122 8-bits, like A low plus B low will be equal to C low plus some of the carry on like into the next high 128-bit, and then do the similar things for the high 122 8-bit additions here. And then further, what you need to do is you need to prove that the word A, B are correctly popped from the stack, and then the output C is correctly pushed back to the stack. So what you're going to do is you introduce an additional lookup table that help you as an auxiliary data structure to help you to prove any stack or memory operations here. So here, what you're going to do for proving the stack pop is that you just do a lookup, thinking like so I'm pop up like the stack at a certain stack pointers with its read, and then that's all going to like the value you are going to pop up from the stack. And then after you do the calculation of the word C here inside the circuit, you're going to push back, push the stack back and write back to the correct address inside the lookup tables. And because this lookup tables is also constrained, it's also constructed after the executions, so that you need to have additional circuit to constrain that the lookup table is constrained correctly. So this is like some of the just high-level explanation of the building the zkEVM circuit. There'll be like a lot more details, but if you're interested, you can definitely look at the open source repo to dive more deep into how the code is constrained there. But just give you a high level of the architecture of the zkEVM. So the zkEVM, although we call it a circuit, but actually it constructs with a lot of sub-circuits together to function together, constrain together, such that it can be built to constrain all of the executions happen in the Ethereum virtual machine. So in the beginning for the zkEVM, you have the core part is the EVM circuit serve as the state machine to constrain each opcode that happen like inside the Ethereum virtual machines. But for some of the zk unfriendly opcodes like the AND, OR, XOR, those bitwise operations, the exponential opcode, and then the catch-up computations, will be relying on like offload those kind of computation into the lookup tables, and that will be further constrained by other circuit to help you to constrain the whole these opcodes. And then second, for any stack memory and storage operations, we'll be relying on a RAM lookup table, as I just showed before. So those like a RAM lookup table that it serves as a database that consists of all of the records of stack and memory and storage operations. So inside the EVM circuit, you don't need to reason about like the correctness of those operations, but you just find a match inside the lookup table, the database of all the records. Now, once you have a match inside those RAM lookup tables, you will consider those stack and push and pop is correctly, the memory read and write is correct inside the EVM circuit. And then you have some additional lookup tables to help you to load correct bytecode from the smart contract, and you can load certain informations from the transaction call data, and then some block metadata from the block lookup tables. So all these lookup tables will be then further constrained by some other circuits to help you to prove that those lookup tables is correctly constructed inside the circuit. And then in order to serve this to constrain, help you to write all of the lookup table circuits, you will also introduce some additional lookup tables and additional circuits For example, there'll be some Merkle patricia tree circuit will be constraining any read or write to the storage and state trees. And then also there'll be some transaction signature circuit, ECDSing circuit, helping to verify the transaction signature is correct. And then there will be some RP encoding for the transaction here. There'll be some RP lookup table and RP circuit. And then finally, you will introduce a public input circuit that's going to connect the public input data that you uploaded with the Rollup, and then constrain like the certain data is correctly calculated in the whole zkEVM circuit. Okay, so lastly, a bit like about Scroll is that we are building the zkEVM with the community, like with a lot of community members. Not only like Scroll is doing that, and we also like having this design, and then all of the code has been peer reviewed by the communities, by the community members from like us and from the PSA team of the Ethereum foundations, and also like other many more people like who are interested in the zkEVM and then contributing to the zkEVM repos. And if you're also interested, you can also take a look at the repo, and then we'll welcome you to contribute to the same repo together. And then lastly, about like our principles, like while we are building the zkEVM to scale the Ethereums, we still like follow our principles when building things. First, we aim to build an EVM equivalent zkRollup so that it can achieve the best-in-class user and developer experience. And second, we still like to keep a security-first mindset when building the layer 2s. So we first have the zkEVM and zkRollup protocols that can explicitly prove the correctness of any executions and transactions on the layer 2. And then we also actively having this external and internal auditings on our code base, and also being building with the community, building like in the open, so that like all of the code can be also peer reviewed by others, not only like us building like in-house code. And then third, we also believe in the decentralization matters in the layer 2 context, which we think like it will be the key property of the blockchain to be censorship resistant, and then to be also social resistant, so that we are committed to decentralize across all different layers, including we're having a decentralized prover network and a decentralized sequencer or validator network. And then last, like I will just talk about like we also have like a hackathon bounty program in this event. And then we will have 3 different tracks. First, we will ask you to deploy your smart contract on top of the Scroll testnet. That's a public testnet on the Gertie. And then the deployment process will be just very similar to what you do on the top of the Ethereum. You only need to change RPC endpoint. And the second is that we love zero knowledge. So show us your best application building new use cases that leverages the power of zero knowledge proofs. And the third track is that we want to see the developers and dApps taking advantage of the cheap gas fees and a faster block time on the layer 2s. And you can benefit from the layer 2 scaling property and a faster finality with the zkRollups. And I hope you enjoy like the hacking on top of the Scroll testnet. And for more information, you can also check out this website. Okay, that's all about like my talk. And thank you everyone for listening to the talk. Again, I can take any questions from the audience.
That was awesome. That was such a good overview on how everything is set up. We don't have enough time for questions because I want to make sure that we can get to the next talk. There's a time constraint on the other end, but I'd love to kind of maybe just ask you one little thing as we get the next speaker set up, which is if you have a wish list of what you would like people to build on Scroll or just on zkEVM. Is there something that you've been really wanting to see that you haven't seen yet, or you think there's something that other people should try? What's on your wish list?
Yeah, that's a good question. So I think the wish list, like we are seeing like that. I think like the zkEVM is building like for general purpose. So any type of applications, any like innovative like the applications can be also like built on top of that of the Scroll zkEVM layer 2s. But like I think like some interesting thing would be you can think of like any zk applications that be interesting, like privacy or like any private votings or any like this like social application like identities, like those applications I think will be innovate like the more easily on the Scroll.
So that's an interesting point. So maybe I also misunderstood. How would private voting work here? Is it just the fact that you don't get to see the weights, or like where's the privacy coming from in this example?
Yeah, so like to just clarify, like actually the zkRollup usually doesn't provide privacy by default. So it's like it's more for the scaling and the compression of the transaction happen. But for like any private applications, you're probably like having the private shield pool so that anyone you can hide the identity of like the voters, so that you don't need to review your vote, but you can still verify that someone in the pool in the DAO like voted like and only you can only vote once.
So existence checks on like making sure that nobody's abusing it and having that information be private.
Yeah,
that's awesome. Yeah. Well, thank you so much. And with that, we are ready for our next talk. So go hack on Scroll and we'll see what people built.
Thank you. Thank you, Captain.